By the end of 2026, many researchers expect to declare the arrival of artificial general intelligence. We've reached a point where the core scientific breakthroughs needed for AGI have already been achieved. Now, progress is largely a function of how much compute and data we can feed into the system. This creates a sharp divergence. On the left, algorithmic capability follows an aggressive exponential hockey stick curve. But on the right, global electrical grid capacity and semiconductor output remain on a flat, linear trajectory. This gap is the infrastructure bottleneck. The math suggests we are ready for superintelligence, but the physical world is lagging behind. We currently lack the raw global energy and the specialized silicon required to deploy these models at scale. To understand the macroeconomics of the next 36 months, we have to look past the software and track 5 specific megatrends that are currently restructuring the physical foundations of the global economy. We can map these trends through a framework called the AGI stack. It builds upward through 5 distinct layers: intelligence, space, physical infrastructure, capital flows, and finally, the societal transition. Success in the next decade depends on mastering the mechanics of this stack, as it forms the bridge between our current economy and a state of post-scarcity. At the base of the stack is the intelligence layer. We are seeing a phenomenon called benchmark saturation, where the standard tests for human-level reasoning are being routinely maxed out by new frontier models. Consider the GDP eval benchmark. In direct comparisons, GPT 5.2 successfully automated 71% of professional knowledge work tasks across 44 different occupations. It did so at 11 times human speed and at less than 1% of the cost of a human professional. These models have moved into a phase of agentic reasoning. They can now handle multi-step execution, autonomously navigating complex projects that previously required human oversight. Frontier labs are leaning into this capability, prioritizing the development of autonomous agents that can act as a core subscription for every aspect of a user's digital and professional life. This enables recursive self-improvement. Because these agents can write and debug code, they are now being used to optimize the algorithms for the next generation of AI models. This creates an exponential feedback loop. As the AI helps design better versions of itself, the cycle of improvement accelerates, shortening the time between each major capability jump. With 71% of specialized tasks already automatable at a fraction of the cost, the bottleneck has shifted. The constraint is no longer the code, it is the physical world. To bypass terrestrial constraints, we move to the expansion layer. Hyperscalers are increasingly looking toward orbital infrastructure to sustain the growth of AI scaling laws. Expanding on Earth is becoming difficult due to 2 specific limits. First, the sheer physical real estate required for gigawatt-scale data centers is vanishing. Second, our atmosphere has a finite thermodynamic capacity to dissipate the massive heat loads these clusters generate. Orbital data centers solve both problems. In the vacuum of space, heat dissipation is more manageable, and a solar synchronous orbit allows for the capture of unfiltered solar energy 24 hours a day. This orbital built-out is enabled by the current monopoly on heavy-lift, reusable rocket technology, which has drastically lowered the cost of ferrying server hardware into low Earth orbit. A geopolitical race is now underway between U.S. commercial entities and the Chinese state to secure the prime orbital slots and raw materials required for these space-based compute clusters. Consequently, the control of orbital energy and compute capacity is becoming the primary lever of geopolitical power. Down on the physical layer, we face the warm rack dilemma. The industry has the GPUs, but it lacks the grid power to run them. Major tech hubs are currently seeing their energy demands outpace the capacity of local electrical grids. This global heat map shows over 5,000 data centers currently in operation. To power the next generation, companies are bypassing the public grid, routing $500 billion in private capital into dedicated natural gas and nuclear nodes. This is driving a nuclear renaissance. Tech companies are now the primary funders of small modular reactors, or SMRs, and advanced fusion research, seeking a dense, localized baseload power source that doesn't rely on the legacy grid. Nuclear power is the only terrestrial source capable of providing the constant, multi-gigawatt energy supply required by a single frontier AI training cluster. Beyond energy, the physical layer is gated by the chip wars, the absolute reliance of the global economy on a handful of specialized semiconductor fabrication plants. These foundries are some of the most complex structures ever built, using extreme ultraviolet lithography to etch billions of transistors onto silicon at a scale where a single speck of dust can ruin the entire process. Because most high-end fabrication is centralized in Taiwan, the supply chain is fragile. This has forced the U.S. to use export controls to protect its lead, while China fast-tracks its own domestic semiconductor industry. In this environment, raw energy generation and silicon fabrication capacity have become more valuable than traditional currency. The capital layer analyzes how these physical requirements are restructuring corporate finance. The cost of building AGI is so high that it is fundamentally shifting how companies allocate their cash. We are seeing a massive diversion of free cash flow. Hyperscalers are slashing operational expenses, like human labor and corporate overhead, and redirecting those billions into capital expenditures, chips, robots, and data centers. This shift enables the AI CEO model, where a single human founder can manage an entire multi-billion-dollar enterprise by orchestrating a fleet of specialized AI agents instead of a human workforce. Because agents operate at digital speeds, they cannot settle transactions through legacy banking systems that rely on manual state-backed fiat. Autonomous systems require cryptographic ledgers. Decentralized networks like Bitcoin provide native financial rails for the machine economy, allowing instant, verifiable, machine-to-machine payments. Cryptography also solves the proof of human problem. In a market saturated with autonomous agents and deepfakes, cryptographic signatures are becoming the primary way to verify a human identity. The speed of this new economy is making traditional capital markets obsolete, replacing them with a protocol layer built for agent-to-agent commerce. Finally, we reach the societal layer. The convergence of these technologies is leading to a massive, permanent displacement of human labor. This graph tracks the cost of labor. As AI and robotics scale, the market value of human work is being pulled toward the marginal cost of the electricity required to power a machine. This is the abundance curve. When the cost of intelligence and the cost of physical labor both toward zero, the core economic incentives that have driven human society for thousands of years begin to change. Hardware is reaching a point of parity with software. Industrial robots can now perform high-precision assembly tasks at blistering speeds, operating 24 hours a day without the overhead costs of a human workforce. As labor value decouples from productivity, governments will be forced to transition toward models like universal basic income or universal basic services to maintain social stability. However, this transition also means the deflation of scarcity. When the cost of production for intelligence, medicine, and energy reaches near zero, the basic cost of living drops proportionally. The social contract is being rewritten. The primary challenge of the next generation will be the equitable distribution of the productivity generated by this infrastructure stack. When you view the AGI stack as a single integrated system, the full macroeconomic picture becomes clear. This massive infrastructure build-out is the physical mechanism for engineering a permanent deflation of economic scarcity. As the primary inputs of production, labor and energy, reach the marginal cost of the sun and the atom, the traditional relationship between capital and labor is being fundamentally transformed. The next 36 months will be defined by high friction. Legacy systems will resist this acceleration, and geopolitical tensions over these new infrastructure assets will continue to rise. We are watching the emergence of the economics of abundance. Surviving this transition requires more than just faster software. It requires anchoring your strategy into the physical base of this new infrastructure stack.